we'll talk about that. So that's one of the things. All right, so yesterday we were looking at classifying isomers. So I gave you a handful of examples. The first one, we said that they were constitutional isomers for the two possible isomers because they have a completely different connectivity. They don't have stereocenters, so we didn't have to worry about that. And they were both achiral. Then we went into more complicated examples where we ran into a pair of enantiomers. Those were mirror images of each other. One was R, one was S. And then down here we saw a harder example with 2-bromo-3-chlorobutane and a bunch of different conformations. You can see down below we labeled sets of diastereomers, and on top we labeled sets of enantiomers. I did want to show you a trick anytime you're dealing with something like this. If you notice, 2-bromo-3-chlorobutane, regardless of how you draw it, has two stereocenters. So you can actually use a mathematical formula to figure out the maximum possible set of stereoisomers. So let's write that down. So trick, I'm going to go up here. The maximum number of stereoisomers equals 2 to the n power, where n equals the number of stereocenters. So in the above example, we had two stereocenters, right, labeled with stars. So 2 raised to the 2 power is going to be 4. So 2 raised to the 2 power means at most we could have 4 different stereoisomers for this molecule, right? What if you have 3 stereocenters? How many could there be? 8. What if you have 2 million? You probably need a calculator to figure that one out. These get really, really complicated the more stereocenters you add to them. So just be aware that you can use this trick to find the maximum total number of stereoisomer combinations that are possible. All right, so I'll show you a couple of more tricks. Actually, let's do one more, and then I'll show you tricks. All right, for our next example, let's do 2,3-dibromo-butane. And let's try to determine all of the possible stereoisomer combinations that we can get for 2,3-dibromo-butane. So I'll give you a minute to work on this one. And I'm going to go ahead and draw the skeleton structure. So we know butane's 4 carbons. How many possible stereoisomers could we have maximum? 4, right? 2 raised to the 2. So we could have 4 different possible combinations at most. All right, so maybe the first one, both bromines coming off position 2 and 3 are wedges. Maybe for the next one, they're both dashes. Maybe this one's a wedge and one's a dash. Or maybe the first bromine's a dash and the second one's a wedge. All right, so going down the list, we've drawn all 4 possible isomers, the maximum combo we can get. Determine which of the following isomers are chiral or achiral. So do you think the first one's chiral? This one? Is there an internal plane of symmetry? No. Well, let's try. So let's say I rotate the sigma bond around, right? If I rotate the sigma bond around, the bromine on the left is still going to be a wedge. What will the bromine on the right be? It would be a dash. Does this have an internal plane of symmetry? No. So this would be a chiral compound, right? If you don't have an internal plane of symmetry and you have stereocenters, you've got to be chiral. Okay, so this one must be a chiral compound. What about the second one? Yes. All right, what about the third one? No, it is achiral. If you imagine spinning this sigma bond, like we saw the other day, you could have one bromine here that's a wedge, and when you rotate that methyl group into the down position, the other bromine is going to stick up, and it's going to become a wedge as well. This has an internal plane of symmetry, and therefore it must be achiral, right? Okay? So this would be achiral. What about the last one? Achiral. All right, so let me ask you about this one. This one I shouldn't have erased that. If we did that sigma bond rotation, we said that it could be represented by this. That gives you the internal plane of symmetry. This one, similar idea. We can do a sigma bond rotation. That gives you this compound. Both of these have an internal plane of symmetry, so both of these must be achiral, right? Agreed? All right, what's the relationship between those last two? Ah. So let's take our imaginary pancake flipper. We're going to grab one of them, flip them upside down. To me, they look identical, right? They're just upside down versions of one another. So really, these are identical compounds. So what I'm going to do, I'm going to just go ahead, mark this up. I'm going to, down here, write these are identical compounds. So if you go back up and you look at my trick that I just gave you, the trick I gave you said the maximum number of stereoisomers is 2 raised to the n power. However, that doesn't mean you're always going to get that. That just means that's the most you could theoretically get. There are some situations where you run into identical compounds. All right, so if we look at these ones, we now need to designate R and S on each of these. So let's go ahead and take a look at this one. What's that stereocenter? Is it going to be R or S? Let's say R. What about this one? Is it? So bromine would be the highest priority, followed by the carbon on the left, followed by the methyl group. So I'd say that's going clockwise. This should also be R. What about this stereocenter? S. What about this one? S. What about this one? R. And this one must be an S. Okay, so we've got our 3 possible isomers. All right, now we need to classify these with a bit more detail. Okay, so when I look at these two, so the first isomer and the second isomer, what's the relationship between these? I'd say they're enantiomers, right? They're mirror images of one another, but same connectivity. So these are enantiomers. All right, and then what about between the first and the third one? I'd say they're connected in the same way, but they are not mirror images to one another, so these are diastereomers. All right, if we look at our third compound, is there an enantiomer to that third compound? Meaning, is there a mirror image? So does this compound right here have an enantiomer? Well, we kind of drew it. It was that identical compound that was the fourth one. So its theoretical mirror image is the exact same compound. Therefore, it has no enantiomers. This is referred to as a Meso Compound. Yeah, it's because it's achiral to begin with, which means it's superimposable on its mirror image, right? So let's make a note about Meso Compounds. A compound is meso if it has more than one stereocenter but also has an internal plane of symmetry. Let me zoom out a bit. It's also important to remember that meso compounds must be achiral due to that internal plane of symmetry. So they're kind of the weird oddball stereoisomer examples where they aren't chiral even though they have stereocenters. Does that make sense? All right. So I did want to show you a few tricks for identifying diastereomers versus enantiomers versus meso compounds. These are pretty reliable. However, the ultimate check is that mirror image check. So I'll give you some of the useful tricks. So tricks. For enantiomers, it's pretty easy. Enantiomers are a pair of compounds where all of your stereocenters are flipped. But your connectivity is the same. Okay, so let's take a look at what I mean by this by going back up to our previous example. And we'll look at the enantiomeric pair that we had. So do you see the enantiomers that I've labeled in blue? Those were the first two compounds. And the first one, it was RR. The second one was SS. So both of those stereocenters were flipped in order to make the enantiomer, right? So anytime you have a mirror image, that stereocenter will also have a mirror image for the stereochemical designation. So what was R will become S, and what was S would become R. Make sense? It only works if all of them are flipped. If you don't flip all of them, they're not enantiomers. Okay? That leads me to the next one. Diastereomers. That is a pair of compounds where some, but not all, stereocenters are flipped. But your connectivity is the same. All right, so let's again go back up and compare our diastereomers. Yeah?
I just have a question about the Meso Compound. You said they all could be flipped. If we just had a hypothetical compound that had orientation was RRSR, and it became SSRS, it'd be a Meso Compound still?
Not a Meso Compound. Are you thinking of enantiomers?
I'm maybe getting them mixed up.
Well, we'll take a look at a few examples here in a minute, but let's first look at the diastereomers. So up here, the diastereomers were the first and third, so it's comparing our Meso compound, that third one, to the first one. Do you see how the first position remained as an R, but the second position we flipped R to S? So we only flipped one of our stereocenters. We didn't flip both of them. Immediately, we can look at this and say, well, we flipped some but not all, therefore they're diastereomers. It's a pretty simple trick without needing to worry about mirror images. All right? Last but not least, let's identify meso tricks. A meso compound is a compound with more than one stereocenter the left and right hand side are the same. Sorry, let me zoom up a bit. But the stereocenters on the left are opposite to those on the right. So we're not looking at a pair of compounds anymore. We're looking at a single compound. We're saying the left-hand side of that molecule is the same as the right-hand side, and the stereocenters on the left have an opposite stereocenter on the right. Does that make sense? So a meso compound, for example, will never have two S stereocenters. It will never have two R stereocenters. However, if you've got an R on the left and an S on the right, maybe it's a meso compound, assuming that the left-hand side is the same as the right-hand side. Does that make more sense? And we can go up and we can confirm this with our example, right? Our meso compound, we had the left-hand side about the same as the right-hand side, and the stereocenter on the left was R, stereocenter on the right was S, so they're mirror image stereocenters to one another. Does that make sense? So these tricks can be pretty useful. All right, do you want to see a few examples of this and test out your ability to spot identical compounds, meso compounds, and enantiomers? All right. All right, so for this one, let's do this one. So are these enantiomers, diastereomers, meso compounds, constitutional isomers? How would you relate these two compounds? What I normally like to do is compare the names. So let's go ahead and compare the names. So this one, I would number going left to right. And we've got a stereocenter right here. Would this stereocenter be R or S? I'd say this would be S. We've got a stereocenter on carbon 3. Would that be R or S? R. Okay, so let's name this. We always, for our prefix, designate our stereocenters. So we put 2S, comma, 3R. That designates our stereocenters. We put that in parentheses. And we'd say 3 bromo, 2 chloro, pentane. Now let's compare this to the second compound. All right, the second compound, should I number going left to right or right to left? Right to left. So I go 1, 2, 3, 4, 5. All right, we've got a stereocenter for the bromine. Would that be R or S? R. All right, what about this one? S? All right, so for this one, we could go ahead and name this just like before. Let me clean this up. So this would be 2R, 3S, 2 bromo, 3 chloro, pentane. All right, students will look at this and they'll say, well, position 2 was flipped from an S to an R. Position 3 was flipped from an R to an S. Shouldn't these be enantiomers? Why not? They don't have the same connectivity. So constitutional isomers, the root or the parent is completely different from one another, right? So these must be constitutional isomers. One has the bromine coming off of carbon 2. The other one has it coming off of carbon 3. So these are constitutional isomers. All right, let's do another one. right, so we've got two different groups, or sorry, two different molecules. We could go through and name this as well, but I'd say these definitely have the exact same connectivity, right? All right, without even assigning R or S though, do you think these are enantiomers or diastereomers? I would say diastereomers. If you notice, this position and this position are exactly the same. So we didn't flip that one. We didn't flip this one either. However, we did flip this one. So we flipped one of the stereocenters, but not all of the stereocenters. Therefore, it must be a set of diastereomers. So let's make a note of this and just say this position was not flipped. All right, let's do one more and then we'll switch gears. Or sorry, shoot. This one was flipped. Holy cow. Only one position was flipped. My brain is not working right today. So we didn't flip all the positions, we only flipped one of them. Yeah.
The top carbon, if we were doing stereoisomers, would that be considered one or no?
So the top carbon, is that a stereocenter? Yeah. Let's try to assign R or S to it. So highest priority, do you think it'll be the lower left carbon, lower right carbon, or the methyl group pointing up? I would say the lower right carbon. So this would be priority 1. That carbon is attached to 2 other carbons. None of the other carbons have a 2-carbon attachment. Followed by position 2, followed by position 3. So that would that be R or S? I would say R. So you can assign a stereocenter there. Good question though. All right, let's do one more. Sorry, that's not the greatest wedge I've ever drawn. So let's look at these. All right, they do have stereocenters. So let's assign that stereocenter. That can be R or S. It'd be R. All right, what about this stereocenter? Make your head spin. All right, so we put priority 1, whoops, up here, priority 2 down here, right? Priority 3 here. So we're going to the left. However, we got to flip it because that assumed hydrogen is going to be a wedge. So this would be an R. All right, so now let's back up and look at the other one. Got a stereocenter here and a stereocenter here. Let's determine the stereocenter, whether or not those stereocenters are R's or S's. So this one on the left, is that going to be an R or an S? S? What about the one on the right? It's going to be an S. Okay, so we've assigned stereocenters here. It looks like what was RR is now SS. So what does that mean? They're enantiomers. So that's my trick, is if you're ever in a pinch and maybe it's flipped upside down, spun 10 ways to Sunday, name the molecule. If the root of the name is different, that means you're dealing with constitutional isomers. If you flip some stereocenters but not all of them, that means they're diastereomers. If you flip all of your stereocenters, that means they're enantiomers. So pretty simple trick you can use for identifying a lot of these. My last question, are these Meso compounds? No, they're not. If you remember, like I was saying, a meso compound can never be RR. It can never be SS. The stereocenters need to be reflected on the left-hand side versus the right-hand side. So these are not meso compounds. Each of them would be chiral. All right. Yeah?
Meso compounds also don't have enantiomers?
And meso compounds do not have enantiomers. If you tried to draw the enantiomer of a meso compound, you're actually just drawing the same compound. So there's really no such thing as an enantiomer for a meso compound. Great question. Yeah?
So can meso compounds only have 2 stereocenters, or do you just have to have an even amount?
They have to have an even amount. That's a great question. Or actually, I shouldn't even say an even amount. Let's back up. I'm thinking of an exception to my own rules. So let's take this compound, right? This would be an example of a meso compound because it has an internal plane of symmetry. So you can have any combination of stereocenters, but you have to have a symmetry element in that molecule. All right. So let's talk a bit about cis and trans isomerism and how that relates to R and S, because that confuses people pretty badly. So the question is, why would we use R and S if we can use cis and trans? We've used that before. So let's define cis and trans in a bit more detail. This is called geometric isomerism. It is not absolute. When we designate a stereocenter or R as S, that is absolute. You cannot refute it. You cannot argue it with anybody. It's true, right? Let's take a look at this example, and you'll kind of see what I mean. So let's say we have this compound versus this compound. First of all, are they enantiomers or diastereomers? Diastereomers. If you see, we flipped the top stereocenter, but not the bottom. All right. Next question I would have, is this a stereocenter? The red star? Not really. We can't assign its absolute configuration as R or S because it doesn't have 4 different substituents coming off of it. All right, so we can't assign either of these as R or S, which makes our lives a bit trickier. This is an appropriate situation for using cis and trans, right? If you can't use R and S, use cis and trans. So the one on the left would be cis 1,4-dimethyl cyclohexane. The one on the right must be trans. Let me slide this over. And the reason we use this is essentially we can't assign R or S. However, these are different molecules, so we need to differentiate them using a naming convention. Yeah?
So would they not be diastereomers because they're not?
That's a good question. So the question was, are they diastereomers? Yes, they are still diastereomers, even though we can't assign absolute configuration. They have the same connectivity, but they're not mirror images. Yeah. All right, let's compare this to another example. All right, in the second example, what's the relationship between these two compounds? These are enantiomers, right? If you look, we flipped all of our stereocenters in both of these. The top one, we only flipped one, so the top one was diastereomers. All right. If I look at both of these lower examples, though, they both look trans to me, so why can't I just name them both trans 1,2-dimethyl cyclohexane? It doesn't tell you which enantiomer you have, right? So let's make a note of that. So saying trans 1,2-dimethyl cyclohexane is ambiguous. Oh man, my handwriting is terrible today. Is that how you spell ambiguous? It always looks funny.
The spelling is ambiguous.
The spelling is ambiguous for ambiguous, so we'll leave it as is. So saying trans 1,2-dimethyl cyclohexane is ambiguous and doesn't specify which enantiomer you have. What would be a much better system for naming these? Yeah, use R and S. Then you can clearly say I have one enantiomer or I have the other enantiomer. So when you run into these situations, use R and S designation or naming to specify. So I always tell people use R and S unless you're in a situation like the first example where we can't. And then you need to use cis or trans, so that they are kind of confusing that way. Does that make sense? Yeah.
How would you determine which is the highest priority one?
Yeah, that's an excellent question. So let's actually try to assign R and S. So let's do this one first. So what's this stereo center? Okay, so that would be an R. What about this one? It would be R, right? So that would be 1R, 2R, 1,2-dimethyl cyclohexane. Versus this one over here, what would this stereo center be? It would be S. And this stereo center? S. So this would be 1S, 2S, 1,2-dimethyl cyclohexane. So that's why I say naming is really important for distinguishing the differences with some of these. It can make your life a lot easier. Otherwise, people look at this and they're like, well, they're both trans 1,2-dimethyl cyclohexane. Shouldn't they be the same molecule? No. We need to be more specific than that. Great questions, though. All right. So let's jump into kind of, I think we're going to skip the alkene one. We'll do that when we get into alkenes. I don't think that's even included in your sapling. So we'll talk about purification and isolation of stereoisomers. All right, so trying to separate or purify stereoisomers sometimes is non-trivial. Sometimes it's really easy. It depends on the isomer. So which isomers are easy to separate from one another? Constitutional isomers? So constitutional isomers are easy to separate or easy to purify. And why is that? They have different physical properties. Right, so we saw all the way back, I think in week 1, some constitutional isomers maybe can H-bond while others cannot. So you can purify those, no problem. They're radically different. All right, what about diastereomers? Are diastereomers easy or hard to separate? Does anybody have a hypothesis? I don't know. I'd say diastereomers could be very different from one another. They're not mirror images. They're actually pretty easy to separate for most industrial situations. So diastereomers are easy to purify too, because they also have different physical properties. So for example, you could maybe distill one diastereomer away from the other or vice versa, or maybe you can crystallize one and not the other. So there's a bunch of different techniques you can use to purify diastereomers. Enantiomers are the bear. These are not easy to purify. They have the same physical properties. All right, however, I started out this chapter by describing drugs where one enantiomer was the effective one and the other one might kill you. So if you're working in a pharmaceutical production facility, that's a big deal. You need to purify your enantiomers. So then the question is, well, how do they do that? All right, so there's a couple different ways. So to purify enantiomers, there are options. Let's go over some of the options. The first one is arguably the hardest. This is crystallization. So you can crystallize each of them. Each enantiomer has a unique shape. What do you think the opposite enantiomer looks like? The mirror image of that exact same shape, right? And so what they did in the early 1900s was they would crystallize things like tartaric acid, look at the individual crystals under the microscope, and then they would physically grab them with tweezers and separate them out into little piles. Do you want to do that in lab? No, that would be terrible. So this requires physical tweezing. This is not easy. We'll emphasize that. Nobody would do this. Yeah.
So it's a purify, but if you do like one by hand, and still they look at the microscope.
Yep.
Then would it be some kind of error happen because it's human doing?
Oh, absolutely. So the question is there human error when you're physically trying to tease apart millions of crystals? Absolutely. But this was how they did it in the early 1900s because they didn't really have any better techniques available.
But did they do it when they make it?
No. I'll show you the more modern ones if we have enough time today. So let's talk about number 2. The number 2 route is arguably the easiest. And these involve chiral resolving agents. All right, so I'll kind of show you the general idea. Let's say that you've got a compound that looks like this, where you've got an amine and a phenyl group, and I'll just abbreviate the phenyl group like that. And it's mixed in with this amine. What's the relationship between these? They're enantiomers, right? They're not going to be easy to separate from one another. So if you have these mixed together, the question is, well, what do you do? So you've got an option. What you can do is use a natural chiral source to basically help out with this process. So I'll show you a common one. Oh, shoot. Let me move this down. So this is a carboxylic acid. We know amines are pretty good bases. So if you've got an amine, that top amine could grab a proton, or the bottom amine could grab that proton. You have an equal chance, right? They have the exact same physical properties, exact same pKa, exact same basicity. So either one of those could steal the proton from the carboxylic acid. And let's take a look at what products we would get out. All right, so for the top one, we would get a phenyl group. Our nitrogen now has an extra proton, so that's our cation, but we also need to account for our anion. So this would be one of the salts that you would get out of the reaction, right? A cation anion pair. So that's one salt. The other salt you would get would look super duper similar. So this would be your other possible cation anion pair. So you could isolate a mixture of two different ionic salts, right? What's the relationship between these salts? So let's think about this, right? If we identify this stereocenter, this would be an S stereocenter. Over here, this would be an R stereocenter. We have another stereocenter in our conjugate, or sorry, our anion. And for this one, this would be S. And over here, it would also be S. So the relationship between these two ionic compounds would be what? They're diastereomers. So in order to do this, though, we have to use something that is chiral in that intermediate step. So this is called S-maleic acid. And this is a naturally occurring chiral compound. So you can treat this with maybe an amine, create a set of diastereomeric salts, and then purify those salts, and then just deprotonate your amine when you're done, and you've got two separate pools of pure enantiomers. So this is a pretty common technique. So let's make a note. Diastereomers and can be separated. So pretty common technique. All right, we are running out of time, but I'll briefly explain the last one to you. The last one is chiral chromatography. This is the much more advanced technique. It actually doesn't involve any reactivity. So what you do is you basically shove your mixture of enantiomers down a column, but the column contains some naturally occurring chiral compound on the inside, and one of your compounds, meaning one of your enantiomers, will travel faster than the other through that chiral compound due to the weird handedness interaction between the naturally occurring compound and the other one. That's really, really expensive. Most people don't do that on a very large scale because it's just too cost intensive. The chiral resolving agents are much more common. All right, so that's where we're going to end today. Tomorrow we'll finish up talking a little bit about Fisher projections, and then we might jump into our new chapter.